Our next puzzle will be going from the graph of a sinusoid to its equation. In the process, we'll look at the description of the behavior by using the sinusoidal terminology. Here's our setup. For the sinusoid below, give the period, frequency, amplitude, phase displacement, and sinusoidal axis locations, and then come up with a particular equation for the sinusoid. Here we have our sinusoid. Now, a period is the measure of the distance it takes for the image to repeat itself. Here, the numbers we're given correspond to the maximums or tops of our sinusoid. We go from a maximum at 2 to a maximum at 27. So 27 minus 2 gives us 25, and there's our distance for the period, 25. The frequency, as we remember, is simply the reciprocal of the period. So the frequency is 1 over 25. The amplitude is the distance from our midpoint to either the upper bound or the lower bound. We can see that our upper bound is 55 and our lower bound is negative 31. They don't tell us in the image exactly where the midline is, but we could figure it out. We could also recognize that the distance from the upper bound to the lower bound will be twice the distance from the midline to either the upper bound or lower bound. So, the total distance between the upper bound and the lower bound from 55 down to negative 31 gives us 86 units. Our amplitude would be half that distance because we're only going from the midline. So we divide by 2 and we get an amplitude of 43. There we go. Our phase displacement is a product of our choice of sinusoid, because we want to know how far away from the original behavior at the y-axis we see our new behavior. In this case, the information we're given is all about high points and low points, nothing about behavior on the sinusoidal axis itself. If I look at the graphs of both the sine and the cosine, we can see that our starting values when x equals 0. For the sine, we start at the origin. So our y value is 0 when theta value is 0. For the cosine, we start not at the origin, but at a high point in the behavior of the sinusoid. So if I'm given information about high points in my graph or in my descriptions, I'm much more inclined to use the cosine graph for my model. You'll notice that the two graphs look very similar. The high point that occurs here for the cosine graph is now at 90 degrees for the sine graph. And a low point at negative 180 degrees for the cosine graph is a low point at negative 90 degrees for the sine graph. So we could say that the sine graph is a horizontal translation of 90 degrees to the right of the cosine graph, or the cosine graph is a horizontal translation 90 degrees to the left of the sine graph. So let's go back to our problem and recognize that we are talking about high points, or given information about high points in this problem. So let's use a cosine model to discuss how far we've shifted left or right from the original parent function. Our first high point is here at 2. Which means that our graph has shifted 2 degrees to the right of our original position. So our phase displacement would be 2. Our sinusoidal axis, the last thing we're being asked about, would be halfway between our upper bound and lower bound. And we saw that the distance from the upper bound or lower bound was 43. So if I take that 43 and subtract it from my upper bound, I'll see that my midline or sinusoidal axis is at 12. We now have all the information to form our equation. Our amplitude is our A value. The period allows me to find my B value by taking 360 over the period. Our phase displacement is our D value in the equation, and our sinusoidal axis is our C value. So if I take those values and put them into our equation, we see that y equals 12, our sinusoidal axis, plus 43, our amplitude, times the cosine of 360 over 25, which is the reciprocal of our dilation, times theta minus 2.